Hello, it's David Leroy here, and this series of lecture slides is going to be on the topic of correlation and regression. So, correlation and regression are used to examine relationships between numerical dependent variables and numerical independent variables. And this is different from what we've learnt about analysis of variance, because analysis of variance uses categorical independent variables. For example, in an ANOVA, we might be interested in looking at the relationship between different heights of people, and we might have an independent variable that's called height. We might have one group of people who are in the short condition and another group of people in the tall condition. In regression, we wouldn't bother about categorizing the values that we've obtained into short and tall components. We would simply just use the values that are provided, and that way, if we're using the individual heights without categorizing them, we have a numerical independent variable that is uncategorized. These are techniques that are from the same statistical family as the general linear model, and correlation and regression are very closely related to each other. And correlation and regression are used to answer questions like these. Is there a relationship between IQ and annual income? Is there a relationship between height and IQ? And is there a relationship between somebody's attitude towards the death penalty and how religious they are? So these types of questions can be tackled using correlation and regression. Now, correlation and regression within the field of psychology are mainly used for hypothesis testing. For example, you might have a null hypothesis. There's no relationship between height and IQ. Well, you might be able to then go and conduct an analysis of data in which you've measured people's heights and IQs and perform a rudimentary correlation, and that would start to give you some information about whether there is a relationship there or not. And regression also allows us to do something extra, which is to predict future scores based on the data that we've already collected. So, based on someone's height, can we predict what their IQ might be? With correlation coefficients, there's a couple of important points to remember. The correlation coefficient seeks to provide us with a statistic that tells us something about the relationship between two variables. And this correlation coefficient is always referred to as R. And it can take on values between -1 and +1. If we have a number that is close to -1, that would indicate a perfect negative correlationship, that there is an inverse relationship between the two numerical variables we're correlating together. If you have a R value that is close to 0, it would indicate that there is no correlation or no relationship between the variables that you're looking at. And if you have an R of 1 or close to 1, this is an indication that you would have a very good correlation. We often hear the expression correlation doesn't prove causation. And technically, this is true. Correlation and regression are unable to prove causation, but there are often good reasons to strongly suspect causal relationships. And in this regard, it's really important to think of the theory behind the research questions that you're asking to see if there is some correspondence between the information you're obtaining from your analysis and the reality of what you're looking at. So technically, yeah, correlation does not prove causation. But if we look at different examples, we would have very often good reasons to suspect that there are causal relationships. For example, if we were to collect data from thousands of people about the number of cigarettes they smoke every day, and follow them up to see whether they develop cancer or not, we might find a high correlation between the number of cigarettes people smoke and their likelihood of getting cancer. People who smoke 1 or 2 cigarettes per day may have a very low risk of getting cancer, whereas people who smoke lots of cigarettes may indeed have a much higher risk of getting cancer. So if you see a correlation there, it's very tempting to think that, well, maybe it's smoking that's causing the cancer. Or the alternative argument would be people who are going to get cancer for some reason start smoking cigarettes. One explanation is going to seem more plausible than the other. So correlations, when we observe them, they often allow us to develop our ideas further and then to be able to put those under an experimental spotlight. So with the example for cigarettes that are smoked every day, it might be that you can model cigarette smoking in some other way. It might be that if you want to really test the strength of that correlation, you would have to conduct research with animals and expose some animals to different levels of carcinogen and then measure their prospects of developing cancer later on. Let's look at an example here that illustrates correlation. In this example, people have their memory tested at 2 different points in time. So they'll come into the research lab, perform a memory test, that'll be measured and recorded by the researcher, and then they come back another time and do another memory test. And if you were wanting to perform a correlation, your question might be, well, are the scores on the first memory test correlated in any way with the scores on the second memory test? And here is the equation for correlation. It is saying that the correlation coefficient that you're trying to calculate is going to be equal to the sum of the z scores for each memory test divided by n minus 1. And this requires a little bit of breakdown. If you were to start calculating this on your own, you would first of all need to calculate the z scores for each memory test and then multiply those together and add them all up. We can also see here a plot of the memory scores at both of the times that they were tested. So what can we see here? We have memory scores at time 1, and then we've got those same people's memory scores when they've come back. And it may initially look like these data are all over the place, but what the correlation coefficient is going to tell us is whether there is some sort of linear relationship between the values that we get on these 2 different memory tests. If we perform this correlation and we put this into SPSS and say correlate memory at time 1 and memory at time 2, SPSS will return us with a correlation coefficient of 0.684. And here there are a couple of stars, which indicates it's significant, and it's also providing the significance level. So it's saying that we have a significant correlation and that the value of that correlation looks quite strong because it's close to 1, it's 0.68. So just focusing on those calculations, here is an Excel challenge for you all. If you open up an Excel file and plug in some of these numbers, just see if you can start by calculating for yourself how to calculate your own R square. And I've put some easy numbers into this equation. If you were to open up an Excel file and you put in the numbers that are shaded in grey, you would be able to then go on and add those up. You would be able to calculate the mean, you would be able to calculate the standard deviation, you'd be able to do that for both columns of data. And then you would be able to go on and calculate your z-scores for each of the columns of data, multiply the z-scores together, and then divide by n minus 1, and then this would give you your correlation score of 1. This is a perfect correlation here because I've entered the data so it would end up as 1. So all of the numbers here are simply doubled in this column: 8, 16, 6, 12, 4, 8, and 2, and 4. And what's interesting, once you create your own interactive correlation coefficient calculator, you can start adding in different numbers here and seeing how this R-square changes. And so ask yourself questions like, why is the number always between -1 and 1? Well, by plugging in numbers into these columns here and looking at the different changes, you will be able to start to see that relationship. So what about regression? Well, regression is researchers in a situation where they are trying to make some type of prediction based on information that they already have. And I'm just going to spend a few moments explaining the logic of this. So taking our example where memory has been tested at 2 different times, regression is asking the question, do the scores on the first memory test predict the scores that we're going to obtain on a second memory test? And if you were to enter the same data into SPSS and go to the menu and ask SPSS to perform a regression analysis for you, you would end up with data and output that looks like this. You can see here the regression analysis is producing our R, which is the correlation coefficient, but it's also producing some other information that's going to allow us to try and predict scores. And it allows us to build up this equation, and it's the equation that we can plug numbers into that gives us different predictions for the value of y. So in this example, y would be the score that we're trying to predict, right? The score on memory test 2. And what the correlation regression analysis is showing us is that we can predict y if we take this constant here, (6.652), and then we add that to our value of x that we've obtained, and we multiply that by this coefficient here. And that procedure should start to reliably predict values of y. So, just to break that down, if we were entering data into SPSS, our memory scores at time 1, we've got our memory scores at time 2. We take this equation here, and then for each of these pairs of numbers, we calculate the predicted value. You would end up with these numbers. So what this is saying is that 6.652 plus 15 times 0.56 is going to equal 15.05. And so what we're saying is, based on these numbers and these numbers, we're able to predict all of these individual scores. Now, I showed you a plot before of the memory scores at time 1 and time 2. We're interested to see if there's a correlation. There was indeed a strong correlation. And here we can plot the scores at time 1 versus the predicted scores. So here we're going to plot these scores on a graph with the scores that our equation is predicting based on the information we got about memory at time 2. And what you notice here is a linear relationship. These scores are always going to fall on a straight line when you're predicting memory at time 1 with the scores that are the output of your equation. And that's why we call this linear regression, because we're interested in the linear relationships between different values. Now, that is a simple regression that I have just gone over with you, where we have a couple of sets of scores and we're trying to predict future values of memory performance. But what researchers tend to do is conduct much more complicated regression analyses, and instead of just adding in one independent variable that is numerical, researchers might collect lots of data and want to add in many independent variables into the same analysis. And so if you want to conduct multiple regression that has more independent variables in it, you're going to be using the same logic, but they're going to become much more complicated tests to perform and also more complicated to understand. So researchers might want to collect values of height, weight of individuals, blood pressure, IQ, their EQ scores, and other pieces of information, all to predict what grades someone might ultimately get at university. And the idea behind it is that the more pieces of relevant information that we can get, the better our prediction is going to be. So just a few extra points about multiple regression. Adding more independent variables does mean that you need to collect more data and you need more participants. As a rule of thumb, some researchers say that you need 6 participants for every independent variable that you add. Other researchers think that this is much too low. In any event, you want to make sure that you've got plenty of data, that you're not going to be missing effects that really do exist that you want to discover. So when people do multiple regression, it's often quite exploratory, and people will fiddle with different combinations of variables, trying to find the best model. What variables do we need to put in? What ones do we need to take out that's going to give us our best correlation coefficients? So this means that there's a lot of running and rerunning of the analyses as the researchers try and understand the patterns of data that they're looking at. There are also logical decisions that researchers need to make about what IVs to include. What variables can we put in the analysis? What are feasible? And quite often, really practical decisions need to be made. For example, if you're interested in measuring the effect of stress on exam performance, and you think that stress is going to be an important variable to include in your regression analysis, you may discover that measuring cortisol is indeed the best measurement of stress, but it's also an expensive test that may cost several £1,000s to administer to a large number of participants. So instead you might think, okay, well, we're not going to use the more expensive cortisol measure, but we will ask the participants in the study to rate how stressed they generally feel on a scale of 1 to 10. And it might be that the cheaper variable to collect is just as good or close enough for you to be able to make conclusions about stress on ultimate performance and grades. So that is some basic information about linear regression. There are also examples in the psychology literature of nonlinear regression. And here is a regression equation that is regressing memory scores on this line against the delay. And what makes this nonlinear regression here is that we can see that there's a square root in the equation. And we know that square roots do different things to numbers depending on their size. If we take the number 4 and square root it, the square root of 4 is going to be 2. And that's a decrease from 4 to 2 of 50% of the number. It's just halved. If we were to take a number of 100 and square root it, it would go all the way down to 10. So it's lost 90% of the numbers, and it has decreased considerably more. And so when you have square root functions and other ones like that, what it does is, because it alters different numbers in different ways, you end up with patterns of data that are curvier and more bendy. And quite often in nature, there are non-linear relationships between different variables, and so we would need to be sensitive to that and wonder to ourselves whether we need to be trying to model what we're seeing using non-linear regression.